on the air right now, or?
I think we are.
Oh,
yeah.
Okay. Okay.
Can you
oh, sure, yeah.
get a little closer?
Okay.
Okay. Hi, everyone. This is another episode of On.NET, a weekly show where we talk about .NET with the .NET team and guests. And today we have a guest from the team, actually. Maoni Stephens is with us. Hi, Maoni.
Hi.
So, Maoni, you're an engineer on the .NET team?
Yep.
And you're working specifically on the garbage collection.
That's correct.
Okay,
Yeah.
so tell us about what you do every day.
Well, there's kind of three things I do. One is the feature development work.
Mm-hmm.
Another one is kind of doing performance investigations for our customers and figuring out what is the most important things to do there. And then also we build tools and infrastructure to make that part less painful. So those are three areas.
Okay, how long have you been on the team, if it's not?
Yeah, so when Miguel is here, he asked me that question, and I tend to...
You don't want to answer?
Well, I did answer, but it was kind of a guess, because I tend to forget things that kind of remind me of how long it's been, right? But then I thought, how long have I been working on the GC? And the easiest way I thought was to look at my blog, because
So have you worked on all versions? Let's put it this way. Have you worked on all versions of .NET?
The earliest GC, version I worked on for the GC was towards the end of 2.0.
Okay.
So my very first blog entry was from June of 2004.
Okay.
So it's been 12 years.
We'll put a link to your blog in the video description.
Yeah. Okay.
Very cool. So if anybody has GC questions, you're definitely the person to go to.
Can say that.
Okay, we already have a question from Shmueli. Can we have a book on the garbage collector?
So so there's already a great book called The Garbage Collection Handbook from Richard Jones. He's been writing and updating this book for a long time, and it's kind of the definitive guide if you want to do a GC on your own. So I would encourage you to go read that book.
So that's a book about garbage collection in general. It's not specific to.
So he actually reads tons of papers about other kinds of GCs that people did. So he has like specific descriptions of different GCs in his book. And of course, GC is a heavily researched academic area.
Yeah.
So there's a lot of information just from the academic world about the GC. So.
Yeah, actually, that's really interesting. What has changed in recent years about garbage collection? Are there actually new discoveries? And
so I think, so to me, what makes it really fascinating about the GC is GC, even though it's a pretty old area, I think the first GC was probably written around, it was with Lisp, it was probably around 1960. And people kept researching it. And of course, commercial companies like us, we do our GCs. But because there are new scenarios that keep coming up, you have to keep improving your GC in order to accommodate those new scenarios. So yes, people keep having new mechanisms and tuning for the garbage collectors.
Yeah, we will put the link to this GC handbook book in the description as well. Did you need to make any changes for the GC for .NET Core specifically?
Yeah. So when we open source Core CLR, of course, we start running on non-Windows platforms. So there were specific Windows technology that we were using in the GC that was not available on Unix, Linux, and OS X. So yes, we did have to make changes.
Specifically what?
So this feature that we're using in the GC is called the Write Watch. So it's a feature from the Virtual Memory Manager in Windows. And what it does is you can say, I want you to tell me when I give you a specific range of pages, if anything was written to any of those pages, tell me the addresses of the pages. So we're using that to do our concurrent GC. So when I looked at Linux, actually Linux had a feature that looked awfully like it's specifically for this purpose. It's called the soft dirty bit. So soft dirty bit tells you when the page was written to, right? So if you look at it, you're like, hey, that's exactly what we needed. But unfortunately, we noticed problems with the implementation of that. So first of all, is you need to have the admin capability to use it, and our users are just normal users on Linux. And then also the implementation of it is basically, it just stores the bits in a file. So if you're a super user, you could just write to whatever file on the machine. So we decided to not use that. So in the end, we did a software implementation just solely in the runtime itself.
But the Windows-specific optimizations are still there. So
so it's actually very different. So they take very different approaches.
Yeah.
So we actually tried what the Windows implementation is doing, which is just making the pages read-only. And when you write to it, you incur a page fault. So then you handle that page fault and you make it read-writable. That's kind of how Windows does it, except Windows does it in the kernel. It's very efficient. But we tried that, and we also hit problems with that because Linux has a default limit of the number of mappings that you can have in your process, which is 64K. So if you're so unlucky that you have a different page attribute per page, like in every adjacent page, that means you can only handle up to 256 megs of memory. So clearly that was not enough. So we also abandoned that approach, and we finally settled on the software implementation.
Okay.
Yeah.
Okay. We actually prepared a few questions in advance.
All right.
This one is actually from Miguel. Oh, and Miguel is here, and he's saying fascinating. Well, we can continue with questions from the audience. Have you studied Mono's garbage collector and how they solved that same problem that we just talked about?
I have not studied Mono's GC closely. I'm sure Miguel would be a much better person to talk about that than me. So ask him.
Yeah, actually, if Miguel wants to join us on the call, can do that at any time. Did I send? I'm not even sure I sent the meeting link to Miguel. Let me do that. So before I do that, okay. So another question: have you thought of having the garbage collector be swappable?
I'm not sure exactly what that means.
Yeah, what does that mean?
Swappable means like going to the page file. I mean, we try very hard to not go into page-in situation as all.
Yeah.
Usually what people would
maybe
want
he
to do.
means
or if he meant
right,
choose
your implementation.
So yeah, so if you meant, can you swap our GC out for a different GC implementation? So you can certainly attempt to do that, because if you look at the interface that the GC has with the rest of the runtime, it's a fairly clean interface. So in fact, when we did some versions of the CLR, so we have a few different versions of CLR, some of them, they do have a different interface implementation. So yes, you can swap it out if you want to do the work.
Okay. Okay, so when .NET first launched, developers across the world learned about generational garbage collectors. And that's more a question about going back to the basic principles.
Yes, right.
So can you tell us about how does generational garbage collection work?
Sure.
And how it was originally implemented in
Sure. So the idea of generational garbage collector was when people observed that in a typically running program, you tend to allocate two kinds of data. One is very long-lived. You have your static data that lives on as long as the process runs, and then you have your temporary data. So if you think about a server application, right? Servers handle requests. So the allocations that they make generally live until the end of that request. Then we hope that everything's gone, right? So that's very temporary. So then people had this idea about doing a generational garbage collector where you do not have to scan the whole heap in order to collect garbage normally. So the idea is you only scan the whole heap once in a while to look to see if the static part of the heap has any garbage. But in general, you just look at the younger generation to see if there's garbage. Generally, there is. So you collect that heap, and that makes it very efficient. So there's this concept in the GC world called the card table. So a card is something that you use. You can think of it as kind of a shrink down version of the heap. So a bit on the card table represents, much more than the bit on the heap, right? So the bit will tell you if anything from the younger generation to the older generation has changed. So let's say you do an assignment operation, right? So you say, obj.x equals y. So we'll look to see if y is in the young gen range. And if it is, then we want to record that fact with the card table. So then we set the card for obj.x. Then when we do a young gen collection, we only need to scan the card table to know which references are coming from the older generation to the young generation. So then we can avoid doing this very expensive whole heap collection all the time. So that was the idea of a generational language collector.
But then how does an object get from one generation to the other?
So that's called the survival of objects. So when you collect, say, the .NET GC has 3 generations, right? Gen 0, 1, and 2. So when we do a Gen 0 collection, we look to see which objects survive from Gen 0, and hopefully that's very little. So Gen 1 kind of acts like a buffer for that survival. And then we now mark these objects as part of Gen 1. So that's how you promote or survive objects from young gen to an older gen. Yeah, of course, there's a bunch of perf tuning in the GC that it's not all the time we do that, right? Occasionally we would say, well, looks like you survived very little. And it might be very possible that next time, even when you do a Gen 0 GC, you're gonna see that part of the memory become garbage. So then we would actually prefer it to stay in Gen 0. So there's all sorts of perf tuning in the .NET GC. Yeah.
And as a developer, what can we do to avoid objects being promoted and being too long?
So if you look at a typical C# app, right? C# app kind of, if I look at F# app, they behave very differently. So when I look at our first-party applications, it's the promotion from young gen generally come from a few sources, right? There's a stack promotion, there's GC handles, there's finalized queue, then there's what I call the internal GC promotion. That means if you're holding onto your young gen objects from the older gen, then obviously they would need to get promoted when you're only doing a young gen collection, right? Because if I do only a Gen 1 collection and everything Gen 2 is considered live, so whatever they point to will have to be considered live. Otherwise, when you do a dereference, you just pointing to, right? So so when I look at our typical first-party app, that's actually one of the major sources of object survival. So then we build tools to show you what older gen objects are holding to your younger gen objects. And you can use that to find out, hey, like I didn't know that this younger gen object could be gone, but now I can make it not be held live anymore. So that relieves some burden on the work that GC has to do.
And are those tools available?
So they are. It's called PerfView. You can download PerfView from Microsoft.com. Okay. Yeah. However, I don't believe that. So in order to implement this part, we actually have to have a special version of PerfView because it has to include a bunch of debugging DLs and whatnot. So I don't know if we actually have the public version of this, but we can always look to open source that.
Okay.
Yeah.
And if we have a link, we'll also put that
if you just search for PerfView on Microsoft.com, you'll see a download link.
Okay. Okay, so some are having streaming issues. Sorry about that. will we ever get the ability to hint to the GC about our memory usage?
So we have an API right now called, some of you might have used it, it's called add remove memory pressure. It's the idea behind add remove memory pressure is that when your managed object is holding on to unmanaged object via handle, whatnot, right? So the common scenario for that is like if you have a in the graphics world, if you have a managed object that generally is very small, but you're holding on to like a 4 meg bitmap, right? So GC obviously doesn't know about native part of it. So you can use that to say like, with these managed objects, I want you to also be aware there's this other memory usage associated with it. So people tend to use that in that situation, like WPF. However, that is purely an implementation that's out of the GC. It's on my to-do list to make that be internal to the GC. So GC would actually make that association itself. Another situation is, for example, the SQL folks. SQL folks, they want very tight control in their memory, right? So they want to say, like, if I execute a task, one of the things they do is like, if this particular task is consuming unusually large amounts of memory, I want to kill it, right? So they need a way to measure that. So we have these hosting APIs for people who really want the control in your memory situation. There's a few interfaces. There's iHost Manager, there's iGC, CLR GC Manager, I believe. So you can hint to GC things like, let's say the machine is not under memory pressure, right? So that let's say you have 8 gigs of memory, your physical memory load right now is 20%. But you want GC to think that it's in a high memory load situation. So you could use a hosting API to say, now I want GC to notice there's a low memory situation. So do all your perf tuning as if you're in low memory situation. So that's another way to control the GC's tuning.
So there is a lot more control nowadays over the GC than there used to be.
Well, so hosting API actually has been there for a long time. I think one of the reasons that people generally don't use it is because it does take a bit of work to use it, because you're the one who's loading the CLR yourself now, which is not a problem for SQL folks because they're already doing that. But for a lot of our customers, they think that, I don't really want to be in the business of loading the CLR. And then for people who really want the control, they're like, sure, I'll do that work and get it loaded and then config using these APIs. Yeah.
Do you think it's a good idea to create app domains to help GC?
So I do think it's a good idea to create different domains for the GC, because if let's say you are in a model where you don't have much of a relationship between the older and the young gen objects, right? So let's say you have a bunch of requests that they're fairly isolated, and you can't, if you do have that relationship between older and young gen, you can separate that very cleanly, right? Which means like if you're in a situation where you're referring to everything from everywhere, it's very hard to create separate entities for the heap, right? But if you say I can be in a situation where I'm fairly isolated from each other, I do have this sort of separate memory region concept in my app, then I do think it's a good idea to provide that option. In fact, I am looking into that option right now. So, yeah.
Nice. That's a great question as well. What is the memory debugging profiling story, but not on Windows, on other systems?
So I believe that our profiling API is available in Core CLR. I don't know if there's any restrictions to prevent it from running on Linux Node OS X. I'm not aware of such restrictions. So, which means you can write a profiler yourself and use it as a profiling API. Then the Purview story is very different, because right now Purview uses ETW events to do the perf analysis. ETW is purely a Windows thing. So I know that our performance folks have been working really hard to use the events that come from Linux and then interpret that in Purview. So that's going to ship fairly soon.
So how does the team do it? Because
basically you Linux also has eventing infrastructure, right? And there's also various ways on Linux where you say like, I'm gonna, fire some sort of event. It's just a matter of, interpreting that event and make it, look like the layout, the event is supposed to be interpreted, and then show that in the analysis part in Purview. Okay. So that's a lot of work. So I know that.
So you're gathering the data on each system, but you do the analysis on Windows.
Right. Yeah, that's what we do right now. So the charm about ECW is because it's a Windows-wide technology. It's not just us that are firing events. There's also the OS events. So it's extremely valuable to be able to correlate that. So you can say like, from this timestamp to this timestamp, I have these CLR events. I have these disk I/O events, network events. So you can correlate them to say like, what is it spending the time there, right? I believe on Linux is the same idea.
Okay. So so garbage collection in .NET was introduced from the start 15 years ago. At a time where computers had a lot less memory and were a lot more limited in terms of CPU. So what changed in the way?
A lot.
Yeah.
A lot has changed. I think the CLR has been in existence for probably 20 years, if not more.
20 years.
Yeah. It's been a long time since CLR existed. So we've had, actually different flavors of GC since V1. We had workstation GC, server GC, and a flavor of concurrent GC. So I remember when I first started working on the GC heap was, if you had a heap that was, say, 300 megs, and people would be like, "Oh, what a big heap! Why do you have such a big heap?" Right? But today, if you look at how big of a heap our customers have, it's easily in the multi-gigabyte range, tens of gigabytes range. So that's a huge increase, and we know that the processor speed hasn't increased nearly to that, order of magnitude. So of course, as the heap gets bigger, it presents a wide set of challenges to us. So for example, we used to be 32-bit only, right? In the old days, CLR was only 32-bit. And you're limited by the virtual address space, right? You have 2 gigs by default. You can go up to 4 gigs on 64-bit if you have large address aware enabled. But that's it. That's all you can get. So a lot of our tuning was very much concentrating on how to keep your heap size small. So we wanted to reduce fragmentation. I remember the very first feature I did on GC was to reduce fragmentation. And just so that your heap doesn't go completely out of control, because you'll quickly hit the virtual address space limit, right? And then when we moved to 64-bit, I think Exchange was our very first 64-bit customer. So that certainly presented a different set of challenges, because our tuning, a lot of it was, you have a small segment size, right? I think server GC on 64-bit, the default segment size was 64-bit, 64 megs. So then if you have more CPUs, you get a smaller segment size. So that limited a lot of the tuning. But when you go from 64 megs to, I think our default segment size on 64-bit for server GC is 4 gigs. So if you have more CPUs, you could get to as low as 1 gig. That's a huge jump, right? So we had to do a lot of tuning, because now we're no longer limited by virtual address space. We're more limited by the physical memory. So I did a bunch of tuning for the Exchange folks. And then after that, the problem for years, our problem was, what if you do a Gen 2 GC? Because we didn't have concurrent GC for server GC. And server GC is really where people have much larger heaps than workstation GC. So we really needed to have a better version of concurrent GC for server GC. So that's kind of what I worked on for 4.0, 4.5 to get it enabled. In 4.5, we got it enabled for server GC. So we now have a different flavor of concurrent GC called background GC.
Yeah, it seems like what you're saying is mostly applies to the server GC. What about the other transformation that happened, which is more mobile devices and even Internet of Things devices that are actually getting smaller?
Exactly. You go either very, very big or very, very small. Yeah. So small things, I think, as I mentioned, we have hosting APIs, and people have used hosting API to make more specific changes on their mobile device that tend to have a much smaller memory limit. I believe that's one thing that we do want to work on more to make GC work better for those smaller scenarios. So for example, for HoloLens, what do we do for HoloLens? Because it has very.
But I imagine on mobile, you even have considerations of battery life that.
Oh yeah, of course, yeah, so, right, yeah. So yes, that's one of the areas.
Okay, so we have more questions here. How much of a practical GC speedup is there from using an async programming model to reduce the number of threads?
I think the GC speed is mostly affected by how much you survive, what the relationship is between young gen, older gen, that sort of thing. So, as far as allocation speed, we can allocate very fast. I've seen people allocating, more than many gigs per second. That's okay. But if you talk about the actual GC pauses, I think that's those are the factors that really affect how long of a GC pause you would see. So I think GC on its own actually isn't aware of any sort of async programming model at all. It's purely the async itself that's creating the threads or using the thread pool threads. That's purely an implementation detail from them. So I think if you have more threads allocating, then obviously you're kind of contending on the heap, right? So if you have a server GC, you have 8 heaps because you have an 8 processor machine. So if you have 64 threads allocating, each of the 8 threads will approximately be sharing the heap, right? So but we try to be efficient, of course, to make the contending part as short as possible. So we only take a lock when we absolutely have to. We release a lock as soon as we don't have to be doing stuff that's shared between threads anymore.
That's a follow-up question from what we are talking about server GC. With the emergence of microservices running a lot of small services on the same machine, do we need something that would be between workstation and server GCs?
So I think there's two-fold to this question. So one is microservices. Another one is, do we want to, do maybe combination workstation server, that kind of thing, which is not specific to microservices, right? Of course, microservices, it doesn't have to be small memory consumption. A microservice could consume a lot of memory. It really just means it does a very simple task, right? It does one task that it's good at, but that one task could consume a lot of memory.
But hopefully it will be short-lived.
Not necessarily. It's a microservice idea is really just let's separate the tasks from each other, right? So like if you want to access a database, you go to a microservice that does just that. So it could consume a lot of memory and take a long time. Right. That's purely their decision. But if we talk about if you're running a lot of things on the same machine, then yes, there's a need to then consider what GC flavors you would use. So Exchange actually is a great example because Exchange goes with the multi-process model. So on one machine, they actually have a ton of different processes running. Some of them are for like, ASB app pools, therefore like the store and whatnot. So they did put in effort to decide which processes should be running with workstation, which processes should be running with server. There's another way to do this, which is a few years ago, I worked with another team at Microsoft that they went with for server GC. So you could, because server GC creates the same number of heaps as you have for processors, but there's one note to that, which is it can only use the processors that your process is allowed to use. So if I have 8 processors on the machine and I'm finitizing my process with only 4 of them, that means when I load the CLR with server GC is only going to use 4 GC threads and 4 GC heaps, right? So they went with the model where they just affinitized their different instances of the server with the smaller set of processors on the machine. So that, then they do the load balancing thing, and that's another way.
So in this multi-core world, actually, that's a good segue here. What is the GC doing to keep the CPU busy at all times and do it at the right time?
Yeah, so that's kind of more related to server GC. So server GC, we have multiple GC threads. So we try really hard to keep them busy at all times, right? So if you look at the kind of GC work that needs to be done when a GC happens, there's certain stages, right? So there's, first we go through the mark phase, then we go through this other phase that decides whether we should go compacting the heap or not, right? So these are, at certain points, you kind of have to let the last phase finish before you could start the next phase. So you can't let any of the GC threads still running that are doing the marking before you can proceed, because you want to know all the objects that need to be marked, right? So you need to have those threads finish with marking before you can proceed to say, like, now what do I do with the heap to reclaim objects, right? So there's various mechanisms in the GC that we use. So one of the really cool things about the .NET GC is we have the separation between the perf tuning, which is policies that are enforced on the GC, or by the GC rather, and a set of mechanisms. Mechanisms are things like compacting the heap or sweep the heap, right? So then in our policy, you can say, well, based on these tuning parameters, we want to go the compacting phase, right? Then that's picking the compaction mechanism. So so when we're talking about doing things, keeping the CPU busy at all times, we kind of added these mechanisms that will share the workload between the GC threads, right? So for example, for marking, we can do work stealing between the GC threads. So if one thread runs out of work to do, it can steal work from others. And then we can have, there's a bunch of other things I want to add to make it more parallel. So for example, if we go through the older gen objects trying to find the references to the young gen, again, we could do, like better parallelism there. So that's, and then we have these heap balancing mechanism that says, well, if it looks like you're allocating a lot more on one heap, and next time you make an allocation request, we're gonna go allocate on a heap that's not for your processor. Normally when you make an allocation, we tend to go to the heap that's associated with the processor that you're running on, right? The thread is running on, because it's very natural, right? You go to local processor cache, but we will balance it out if we notice that heaps are very different in how much allocation they've done, right? So that helps with balancing out the work that each GC thread has to do, and then it makes keep the CPU busy at all times.
If you have the same code that is running that measures how long it takes to do something, can we suspend? Oh, can you suspend the GC? Can the developer suspend the GC if he knows that he doesn't want it to happen?
So in 4.6, I introduced this feature called no GC region. So there's various latency modes in the GC. There's low latency, sustained low latency. So this new mode is saying, I'm going to start a no GC region, meaning that I will tell you how much allocation I'm anticipating. So as long as I do not go over that, you don't trigger a GC. Of course, some other thread could still be inducing GCs, then a GC would happen. Or if we notice that we will go into low memory situation, and instead of out of memory, throwing it out of memory, we will trigger a GC. So, but there's limitations on this, how much allocation you can specify when you say no GC region. This is, if the problem is, if it proves to be a problem there, we can lift this limitation. But right now, for example, you can't say like, let's say, don't trigger a GC in the next 10 gigs of allocations. But you could say like, don't trigger a GC in the next 1 gig if it's less than the segment size. And this is all documented on MSDN, where it talks about the limit that you can specify. But as long as you stay within that limit, we will not trigger a GC.
So I want to say we have a lot more audience questions than we usually are, which means that people are really interested by all that stuff. So that's really good.
All right.
And the way things are going right now, I don't think we're going to be able to go through all the questions that we had prepared and all the audience questions. I apologize about that, but are you okay with maybe doing a follow-up in a couple of months or something?
Sure.
Okay. So
no problem.
Yeah, this is clearly a subject that people are interested in, which is absolutely great. Okay, so the next question is, how does the garbage collector handle cache locality?
The way that GC is written today, it actually naturally does that for a lot of the factors. If you think about how allocations are done, right? So as I mentioned, if you allocate on processor 0, right, we tend to make you stay on processor 0. And when you allocate, it's most, a lot of people probably heard of this term. It's called bump pointer allocation. So you have a region of memory on the GC heap, and when you allocate, all you do is you keep increasing that pointer until you run out of that region. So our region for that is about 8K. Sometimes smaller depending on the tuning. We picked 8K, it was for the cache locality purpose. So we did a bunch of experiments and found that 8K seemed to be the best for how much you want to keep the cache warm, right? So we would commit 8K, sorry, we would commit 64K, I think, but we would give you 8K out as something we call an allocation context. So if you look at managed thread, right, I'm talking like on multi-processor machines, because we do have customers on intentionally on one proc like VMs, but most of our customers, I would say, like they're on multi-proc machines. So with each managed thread, you have this region on the thread object called the allocation context for that thread object. So what we do when you allocate is that if you say like new object something that takes 40 bytes, right? GC doesn't give you exactly 40 bytes because that would be pretty inefficient. So then GC would say, I'm gonna give you an allocation context worth of memory, which is around 8K, right? So then the thread will keep that information stored in its allocation context. And then when you make allocations, it would keep on going in that 8K region until it runs out. That's when it would come to the GC allocator for the next allocation context worth of memory. So that kind of, and when we compact, obviously we try to, you can think of compaction as you kind of squeeze out the dead space in between objects and you just, kind of squash the heap, right? So that also naturally keeps the locality in GC objects.
Why is GC allow very large objects defaulted to off in 60-bit processes?
So this is something we added, I think, in 4.5 timeframe. So before that, the reason we didn't allow the very large objects, which are more than 2 gigs, was mostly, it's not exactly a limitation on the GC. It's just a limitation on how the object layout worked. So we have these array indices that was a 32-bit integer. So that defines how much the largest size an object you could have. So before that, before 4.5, we just didn't even, I think we didn't even allow you to allocate more than two gigs, right, as a single object. But then when we added it, because we still did not lift the limitation on the array indices, because that would require more, the JIT changes. And so we kept it off by default. I'd imagine like someday, when we don't have that limitation anymore, we would allow you to allocate a very, very large object.
Classes are currently always allocated on the heap. What do you think about an ability for stack alloc and safe for function local objects?
So I personally, I think that there's definitely merit to that. That's kind of what we need to do to achieve that optimization is to change how the JIT lays out the objects. So that's I think some other runtime they do this, but we have not. But I do believe there's merit to that.
Okay. Does stack alloc reference type?
Yeah, I think that's kind of along the same lines.
Those stack alloc reference types are going to. Stack alloc reference type going to be considered, I think.
Right. That's what I was saying. Like I do believe there's merit to that.
Okay. Why can't we recover from a Stack Overflow exception? So yeah, a little off topic, but do you
Slack or?
Oh no. Well, yeah, that's that's kind of meta talk here, but
Stack Overflow exception is just one of those difficult to handle exceptions that the CLR has to do a lot of work. I think this is probably even before I started work on GC that the runtime team did a bunch of work trying to harden the runtime against Stack Overflow exceptions, because it's just, what do you do when you get a Stack Overflow, right? It's just not an easy exception to handle.
Yeah, and in some cases, one you probably don't want to recover from.
Exactly.
It would be dangerous,
right?
Yeah.
So,
yeah. Okay. We talked about that. Yeah. You talked a little bit about that. What's your current focus on garbage collection?
I think my focus on the GC as a principle is always trying to make GC work more robust under more situations, right? So right now, the .NET GC, because of the sheer number of customers we have, obviously GC already handles a wide range of scenarios, but we want to increase that range. So as we just talked about a few minutes ago, like mobile is a space that we're very interested to make work better, right? Because I do believe that we have room to improve there. So I want to kind of think about, so there's different aspects to a GC performance if you look at it. So there's 3 areas that I call as the fundamental areas of GC performance. There's the throughput, there's memory usage. So then how big is your heap and how much of space is used on that heap. There's also how predictable the latency is, right? Yes. So you could have a GC that gives you great throughput numbers and it doesn't use very much heap size. But if it introduced like very, very long pause here and there, that's very hard to predict. And that's a problem for a lot of people who need to meet their SLA, right? So I really want to take a closer look of these 3 factors and make our GC have more options to handle scenarios that have different requirements on these 3 factors. So you could say, so one of the things I really like about working on GC is GC has a fairly simple performance goal. It's not very subjective. I never heard a person that said, I want GC to be slower, to take more heap size and have more unpredictable pauses, right? But people do have choices where they want to say like, well, I'm willing to trade perhaps a larger heap, but I want to get more predictable pauses, right? That's a very reasonable requirement. So I want RGC to be able to give that choice to people. I don't want to call it knobs, because like when people think of GC knobs, they generally think things that are very specific to GC, right? So like Java GC had a lot of knobs where you could say like, I want the heap size to be X, I want the free space size to be 30%. You know, that's very GC specific. Yes. But I want the .NET GC to be more application specific, which means you want to specify to the GC what sort of application you are. So you can say like, I want to trade this app, because
so
if
you
look
don't
at
also require the
right, I don't want people exactly like that's not a problem that I want our customers to worry about. That's a problem that we need to worry about. But the customer can tell us, well, I'm more interested in having more predictable latency, but I'm willing to sacrifice some on the heap usage, the memory usage. That's very application-centric metrics that people have. So I want the GC to, you know, to have options for that.
Okay, so if I'm an application developer and it's important to me to have that GC latency be always within a certain interval, I can do that?
That is a question that people have been trying to answer for many years. Yes. Yeah. So
and there are some concurrent platforms that are making claims about that.
Right. There's GCs that would say like we have an MMU, it's a minimum mutator utilization that they provide. But it's very common to see a small print that says like we don't guarantee it. Because if you think about it, well, specifying MMU is may not be the best idea, because you know, if let's say I have an application that renders frames, right? I want to keep a 60 frames per second frame rate, right? That means
in gaming, for example, if you have a latency that is too long,
so it means
that you're going to get a freeze on the screen.
Right. So like if which means you get 16.7 milliseconds per frame, but you have that much time to do all your work, right? So I could say I'm gonna let you specify an MMU that says like for every 100 milliseconds I'm gonna allow like a 25 millisecond GC pause. But if you think about the GC doesn't really have any concept of frames, right? So I could incur this 25 milliseconds anywhere. It could be a total frame, right? It's more than the frames total time. So to us, that doesn't really seem like the right choice for the to make. So I tend to think like for our GC, we want the users, if you really want that kind of control, you could tell us when is a good time to trigger such a GC. So that's also something I'm working on right now.
I see.
Yeah.
Interesting. We talked a little bit about tooling, and we're going to provide links if we can about that.
So I wanted to talk. Yeah, let's talk a little bit more on that.
Yes.
So I wrote a set of blog entries on the GC ETW events. I noticed that some people they are using the ETW events themselves instead of using Purview. Purview is a great tool. I use it almost every day myself. We have server application folks within Microsoft that I work with who actually, they would interpret the GC or CLR ETW events themselves. So what they do is, they would collect, CLR ETW events, OS ETW events, and a bunch of other events. When they can say, like, within my request, I can tell you exactly what each part takes. So, I could say, like, network took this long, and GC took this long. So then they can say, what are the factors that would contribute to, for example, my tail latency? So that's something you could do yourself if you really want to have automation on the like to figure out what is taking time on your server or in our.
You want to show maybe?
Yeah. So like we have this internal thing that is called CAP. It's short for Customer Assistance Program. and we have a bunch of first-party customers are enrolled in this. I'm going to show you some pages, but due to privacy reasons, I will show you only the part that's for CAP and not the part that's for that involves any of our customer data. So this is an example of traces from one team where we have this issue diagnostics engine that, based on the common issues I've observed in the past years, it can detect, what sort of issues that you have that we observe from your ECW trace, and what you can do about these issues. So to me, it's not a matter of just detecting something's wrong. Like what do you do to make progress after that? That's extremely important, right? Because only having data and not being able to do anything about it, that's basically makes data pretty useless. So these issues would say, for example, the first issue says excessive large object heap trigger Gen 2s. So then, like, if we clicked on, so I also had an advanced process filtering right there.
One?
So right
here,
yeah. Right. So that, that tells you, like, I want to look at processes that are fairly large, right? Not the ones that are like, takes 10 megs of heap. And then I want to see at least a pattern of the GCs. So I specify a number of GCs greater than 100. So that gives me 179 traces. So if you can click the next tab. So then if I clicked on one of these traces, since it detected the excessive large object heap trigger Gen 2, it will tell you what you can do to make progress. So in the comments, you can say, like, you could use per few, and then you can collect traces and go into the GC heap analyzer view, so you can see, like, who is allocating these large objects. Then it tells you the impact. So you can then say, like, what issue has the most impact on my product, so I can spend time on that issue, right? So that allows people to take a look at their traces, the performance data that send us, and then they can very easily identify what parts that would be most valuable for me to spend my time on, right? Because that's always a problem.
Yes.
People say, like, should I focus on my allocation rate? Should I focus, what should I focus on? So this tells you exactly what is the impact of the top issues that would give you the most bang for the buck if you spend time on them. And then it tells you how to actually make progress. And that's also a part that I'm hoping we can make more and more automated. So, instead of like you going and make progress on them, we can just automatically collect some more data. Then, of course, the idea is, we can get you to the solution as fast as possible.
So this tool that we just showed, that's an internal tool.
It's an internal tool. We love to make this, available to external folks as well. And I'm hoping that will happen someday, right?
So no promises, but we would like this to happen.
Yeah, I do believe that this tool is proven to be not only very useful for the customers, but also very useful for the GC, right? Because, by looking at what the top issues are that people are seeing, then we can make a decision to say, like, how we should prioritize the GC work, right? So which is actually exactly what I did since we had the tool. So.
Yeah, you got a lot of data from that.
Yeah, exactly.
When .NET 4 was in beta, transactional memory support was introduced. However, it was there and then cancelled. Are there any plans to revive it?
Not as far as I know. I think that was a project that went away. And
so can you maybe tell us what that was?
I have never worked on it.
Okay.
So
okay, well, fair enough.
Yeah, it's a completely different feature from the GC.
Okay. Do you have any general advice for developers listening to this about what they can do proactively to?
Right. So I think because I love work on performance, right? This is kind of my passion, and obviously GC is all about perf. So I think as a application developer, I would say the first thing that you want to do is to measure early. You don't want to wait until big designs done, and by that time, if you find a perf problem, it's virtually impossible to change your design fundamentally, right? So that's why we provide perf tools, and a lot of our customers actually, they would have like just a informational level of GC events that tell them, okay, like this is what your perf looks like in general, right? And you better not regress a lot from build to build. So they would, each time, I know a lot of first-party customers at least, they would have perf measurements every time when they deploy a new build. So then they would say like, okay, it looks like something regressed.
So are you saying that we should introduce perf testing as part of our continuous integration test?
Absolutely, yeah.
Very early, so that we can detect
exactly.
fundamental design flows.
The second suggestion I would give is understand the performance characteristics for your primitives, right? So like if I have a feature that I have different parts, like these are the pieces that that my feature consists of, right? Because there's always a question like my feature has these sort of different pieces, and I don't really know exactly which pieces are going to get used the most until I ship my product and probably wait a few months before I see like data come in to say like which pieces tend to be used the most frequently by people, right? So, but it's very important to understand just fundamentally what each piece, the perf characteristics are. It's the same with the GC. So for example, we have these GC benchmarks, and some folks would say like, what is the point of measuring a micro benchmark, right? Because you're not going to see this scenario in the wild. And that's absolutely true. Like if you did that in the wild, then considering the fact that most of our GC tests are just allocating memory, right? It doesn't really do much else. So in the wild, you want to do actually useful work. So, but it's very important to understand how those behave in order to extrapolate when you have a combination of them, how they would react. Because that if you run into a situation that your benchmark represents, it may be not as fast as how the benchmark would manifest it, but it will show up at some point, right? So in your benchmark, it might show up in 30 seconds, whereas on your production server, maybe it'll show up in 30 hours, but it will show up, and you'll need to handle that. So it's very important to understand that.
Yeah, actually, that's interesting, because what you're going to be able to detect in your tests is one thing, but what will happen in production is different. So how do you detect garbage collection problems?
So for example,
in production,
right? I can give you an example. So let's say I take a micro benchmark, right? That you run it for like 10 minutes, right? You observe that the heap does increase. And I look at the increase and I say, is this necessary? Like if it increased because you survived more, that's justified. But if you always survive, in the steady state of it, if you always survive the same amount, you shouldn't have the heap size increase. Yet within 10 minutes, you already have the heap increase. And that's a problem, right? But if you put this benchmark type of allocation pattern in the wild, that increase probably isn't noticeable until like 72 hours later or even longer. But when it starts to manifest itself, you'll need to handle it, right? So the work that we're doing to not have that unnecessary increase, it will benefit your production servers.
I see. So it's about stressing your system.
Exactly. Like when we do the GC test, we are stressing the GC.
I see. Okay, we're almost out of time. Unfortunately, obviously we could go on for hours like that. Okay. What? Yeah, I totally share Miguel's sentiment here. This is really very, very interesting, and not the kind of knowledge that we that is easy to find. So it's really great to be able to share this. Well, yeah, you know what? Let's just stop here. It's 11.
Yep.
So I want to really thank you for being here today. That was
welcome.
Really extraordinary, and I can see that the audience was very excited about that. So
yeah,
thank you.
Of course, and, my pleasure.
I had an announcement to make, actually. Let me just pull that here. I almost forgot, and Beth Massey would have been very upset with me if I didn't mention that. Okay, so there is a .NET conference that is happening. You can go to .NETconf, DOTNETCONF.net. I will put the link in the description. This is in 11 days. We have a great lineup of speakers, including Miguel, who is here on the chat today. And this is happening between June 7 and June 9th. And you have no excuse for not attending that because it is online. So you don't have to book a flight or anything. This is a virtual conference. So .NETconf.net, it's going to be awesome. So register now and watch all those amazing talks. All right. So, well, thanks again. And we'll see you people next week.
Bye.
Bye.